This lecture is on principal component analysis, and we are going to do it on a problem where you can see the answer with your own eyes. We are going to work with photographs of faces. Here is the claim I want to make good on by the end of the hour. Every one of these photographs is stored in 16,384 numbers. By the end of the class, we will store any of them in 15 numbers and you will still recognize that person. Nothing is thrown away at random. 15 numbers are chosen by the data itself. The method that does that is principal component analysis, PCA. It was applied to faces in early 1990s, and the pattern it produces there are called eigenfaces. Faces are the vehicle, not the subject. The same method unchanged runs on gene expression data, on financial time series, on sensor recordings from a machine. Once you have watched it work on something you can see, you can trust. On the data you cannot. Start smaller than faces. 2 measurement per person, height and arm span. Plot one against the other and you get this. The dots form a stretched out sausage running diagonally across the plot because tall people tend to have long arms. The 2 measurements are not independent. Now, suppose you are allowed to keep only one number per person. You would not keep height and you would not keep arm span. You would keep the position along the length of the sausage and how big the person is overall. That single number tells you nearly everything, and the leftover direction across the sausage is so thin that discarding it almost costs nothing. That long direction is the first principal component. Notice what happened. 2 measurements turned out to be one underlying thing wearing 2 hats, and PCA found the hat rack. The whole method is on this line. Find the direction the data actually spreads along. Measure along it, drop what is left. Everything after this is the same move carried out in more dimensions that you can draw. One more thing to notice before we leave the sausage. The direction we kept is not one of the 2 things we measured. It is the mixture of them, roughly height plus arm span. PCA is allowed to invent new axes, and the ones it invents are usually more meaningful than the ones you started with. Before we go anywhere near a face, one word needs pinning down because the rest of the lecture is built on it: dimension. A dimension is one number in the list that describes an object. That is the whole definition. Measure everybody's height and you will have one dimension, one number per person, and the population is a row of dots on a line. Add arm span and you have 2 dimensions, which is the plot we are just looking at. Add weight and you have 3, and the population becomes a cloud in the room. Now keep going. 128 by 128 photograph is a list of 16,384 numbers. So a photograph lives in a 16,384 dimensions. Nobody can draw that. I want to be clear that nothing about that idea needs drawing. The definitions do not change when the list gets longer. A point is still a list of numbers. 2 points are still close together or far apart. A direction is still a direction, and you can still measure how far along it something sits. And here in 3 panels is the whole PCA. Panel 1, take the cloud of data, compute how these measurements vary together. That is the covariance matrix, and we will write it down properly at the end of the lecture. Then find the eigenvectors for that matrix. That is the same sentence to hold on to. PCA is a eigenvector problem. The eigenvectors are directions through the cloud drawn there. Here are 2 arrows. The eigenvalues attached to each one is how much the data spreads along that direction. The long arrow U1 is the direction of the greatest spread. The short one U2 is what is left over, and it is perpendicular to the first. Panel 2. Those 2 directions as new axes and measure each point along them. Nothing has been lost yet. 2 numbers went in and 2 numbers came out. But the number now says something different. The first coordinate carries 98.5% of the variation, and the second carries about 1.5. Panel 3. Throw the second one away. Each point drops onto the line, and the gold sticks now show exactly what that cost. Now every person is a 1 number instead of 2, and the error you accepted is 1.5% you discarded. That is the dimensionality reduction. Keep the direction with the large eigenvalues and drop the ones with small eigenvalues and know the cost in advance. Everything from here is the same 3 steps in 16,000 dimension instead of 2. The only thing that changes is the eigenvectors are the size of the photograph. which is why they get their own name, eigenfaces. And nothing in these three panels mentions faces or heights or arm spans. The method does not know what the numbers mean. Give it any collection of objects written as a list of numbers and it will find the direction that collection varies along. Now jump to the images, and it starts with something that sounds obvious but usually is not. A photograph is already a list of numbers. Each pixel holds one brightness value, 0 or for black up to 225 for white. A 128 by 128 photograph is 16,384 of those values written out in a fixed order. Nothing has been done to the picture on this slide. No pre-processing, no methods. This is simply what an image is. It is worth pausing here because most people think of an image as a picture first and as data second. The rest of the lecture only works once you are comfortable turning that around. The photograph is a list of numbers. The grid on the screen is a convenience for your eye. Here is the idea the whole lecture rests on. If a photograph is 16,000 numbers, then a photograph is a single point in 16,000 dimensional space. Every possible image of that size is a point somewhere in that space. Now try a thought experiment on the slide. Pick those 16,000 numbers at random, you get static. Do it again and again, you get static every time. If you generated random images until one of them looked like a face, you would be waiting longer than the age of the universe. So faces are rare in that space and rare in a very particular way. They are not scattered through it. They sit together on a thin sheet of small structured region because the face is produced by a limited number of things: lighting, head shape, hair, camera distance, expression. PCA's job is to find that sheet, and the rarity is exactly why so few numbers turn out to be needed. Describing a point on a thin sheet takes far fewer numbers than describing a point in the whole space. It is worth putting a number on that rarity. 16,000 pixels, each one with 256 possible values, gives more possible images than there are atoms in the observable universe, many times over. Essentially, all of them are static. A face occupies a region so small that if you could see the whole space, you would never find it by looking. Here is the data. 30 photographs from the Flickr Faces high quality set, cropped to the face and converted to gray. Two things to notice here about how they were prepared. They are lined up, eyes are roughly in the same place in every photograph. That matters more than it looks. Feed PCA unaligned pictures, it spans its first and the largest pattern describing the bubble rather than the people. The same traps appears in every application of this method. If some nuisance shift the data around, PCA will faithfully report that nuisance because nuisance is where the variation is. And they are gray, so one pixel is one number. The color would triple everything without adding any idea. Ask yourself what varies across these 30. Lighting, hair, head angle, expression, age, how close the camera was, how one of those things is going to come back in a few slides as a pattern that PCA found on its own. Step 1, and it is the least sophisticated step in the whole method. Add up all the 30 faces pixel by pixel and divide by 30. That is the mean face and it belongs to nobody in the room. It is the guess you would make about a person if you knew nothing at all about them. From here on, everything we do describes how somebody differs from this face. If you stopped right there, this is what your reconstruction of every person in the set would look like. Same blurry stranger with the average pixel about 16% off. Every pattern from now on is a correction applied to this starting point. Notice what the mean face already tells you. The eyes are sharp because the photographs were aligned and everybody's eyes are in the same place. The hair is a blur because everybody's hair is different. Averaging keeps what population shares and destroys what it does not, which is a useful way to read any average. Here is the answer. These are the eigenfaces, all 29 of them, ranked by how much of the variation between the 30 people each one explains, and with the average face repeated at the end of for comparison. Look at them for a moment. Not one of them is a person. Their patterns brightening and darkening. Mid-gray means no change here. Light areas add brightness when you use this pattern. Darker areas take it away. If somebody asks why they look like ghosts, about half the numbers in these patterns are negative and negative brightness does not exist on a screen, so mid-gray has to stand in for 0. The first 4 or 5 are recognizably face-shaped, and you can see broad lighting and head shape. By 20s, they are edges and features. I'm showing you these before explaining where they come from on purpose. Hold the question of how they are computed. We will do that properly in the last part of the lecture. For now, treat them as fixed set of ingredients. One more property, which we will prove at the end, but which you can see now. The eigenfaces are mutually independent in the sense that no one of them can be built out of others. Each one describes something none of the rest describe. That is why adding them in a sequence keeps improving the answer instead of going over old ground. Now we use them. Same recipe every time. Start at a mean face, then add eigenfaces one at a time, each scaled by an amount that belongs to this particular person. This is one eigenface, E1 scaled by minus 18.2 added to the average. Minus so that the frame is darkened. Look at what we have got. The exposure is roughly right and the face shape is roughly right. The person is not there yet. The average pixel is still 22.5% away from the true photograph. Two things to watch as we click forward. The picture on the left and the percentage at the top, which is an honest measure of how far off we still are. And notice what the amount means. Minus 18.2 is not a brightness and it is not a pixel. It is a coordinate. How far this person sits from the average face along the direction E1 points in. Every number you see above this phrase for the rest of the hour is a coordinate of that kind. 2. The second one darkens the frame around her, still generic. 3. And now something happens. The third pattern begins putting hair on her head and error drops from 21.7 to 17.7%. This is the first frame that looks like somebody rather than anybody. 4. This is her biggest amount of all, plus 22.4 of E4, and you can see what it buys. The dark fringe and the shape of her face arrive together in one step. Error from 17.7 down to 8.7%. 78% of her now is captured from 4 numbers. 5 and almost nothing changes. That fifth amount is only minus 1.7. That is worth a sentence because it is a common misunderstanding. The ranking of these eigenfaces is global. They are ordered by how much variation they explain across all 30 people, not across this one person. Eigenface happens to describe something this person does not have, so for this person it is a nearly free of information. 6. This one matters for this person, 11.6 down to 7.9%. The layout changes here too. 6 terms no longer fit on one line, so from now on eigenfaces stack into a block. 7. The last of the big structural work. 8. And I want you to look hard at this frame because it is the one to remember. 8 numbers carry 93% of everything that makes this person different from the average face. 8 numbers out of 16,000. The 21 eigenfaces still to come will barely change what you see. We are going to click through all of them anyway because watching nothing happen is the most convincing way I know to make this point. But it is in the terms that matter for storage. 16,384 numbers went in, 8 numbers came out plus a set of ingredients that everybody shares. This is a factor of 2000 for a picture that any of us would identify without hesitating. 9. From here you are watching a number fall, not a face change. 10. 97% of the way there. Flip back in your head to 4 eigenface frame and compare. Then you compare 10 with what is about to come. The difference between the 5 and 10 is obvious. The difference between 10 and 20 is going to be almost invisible. 11. Only the percentage is moving. 12. 98%. Each new one is worth a fraction of a percent now. 13. 14. 15. Half of the available patterns, 99% of her. This is where you would stop if storage cost you money. 15 numbers instead of 16,384. 16, 17, 18. If you cannot see any change over the last 3 slides, that is a lesson rather than a failure of the projector. 19, 20. The error is 1.4%, about 1 part of 70 of brightness range spread over 16,000 pixels. 9 patterns still to come. 21, 22, 23, 24. The rest described screen grain and stray hairs. 25, 26, 27, 28. All 29, and the reconstruction is now the photograph exactly. Not close to it, equal to it, to the last pixel. That is not magic. 30 faces live in 29 dimensional space, so 29 patterns can reproduce any of them perfectly. We will do that piece of arithmetic properly later. The number worth carrying out of this sequence is this one. The last 21 eigenfaces, more than 2/3 of the entire set, were between them worth 7%. And it is also worth being clear about what that exactly means. This is not a good approximation that rounds off a photograph. With all 29 patterns, the difference between the rebuilt and the original is 0 at every one of the 16,000 pixels. There is nothing left over because there was nothing outside the 29 directions to begin with. Here is the whole sequence as a table, so you can see it as numbers rather than as a slideshow. Read the last column rather than the first. Going from 1 eigenface to 8 takes you from 22% offered to 93, doubling again from 8 to 15 by 6% points. And 14 after the 14th after that buys 1. This shape, steep, then a knee, and then flat, is the entire reason PCA is useful. Where the knee falls depends on the data. 8 here. On other kinds of data, it can be 3 or 50. What matters is that a knee exists at all. And it is worth asking why the curve has a knee at all, since nothing in the method puts one there. The knee exists because faces are really reproduced by a small number of underlying causes. If 30 photographs had been 30 pieces of static, this table would be a straight line. Each component would be worth the same tiny amount and PCA would save you nothing. The knee is a property of the data. Now the same recipe on a different person, and I want to be precise about what changes and what doesn't. The mean face is the same, the 29 faces are the same, in the same order. Nothing on the left hand side of this slide is new. The only thing that is different is the row number above the eigenfaces, the amounts. His amount of E1 is plus 20.6, where hers was minus 18.2. So watch the numbers rather than the pictures on this pass. This matters for what PCA actually is. The model is the mean face plus 29 face eigenfaces, and it is fitted once from the population. After that, describing a new person costs 1 dot product per component and nothing else. That split is an expensive fit done once and then a cheap measurement per item is what makes the method practical on large collections. 1 eigenface plus 20.6 of E1, where she had minus 18.2. The opposite signs, this person's frame sits on a bright side of the average, while the previous person's frame sat on the darker side. Same pattern, opposite direction. That is what a coefficient does. 2, 49, 3, 66%, 4, still 66%. Compare that to her 78 at the same point. 5, 83%, 6, 7, 8 eigenfaces, 91% of him. Different person, completely different list of amounts, and the same collapse at roughly the same place. That repeatability is the point of running the sequence a second time. 9, 10, 11, 12, 13, 14, 15, 94%, 5.1% off. Everything remaining is texture. 16, 17, 18, 19, 20. 3.7% off, and nothing you can see is still changing. Notice he is stalling higher than she did. At this point, she was at 99% and he is at 97. 21, 22, 23, 24, 25, 26, 27, 28, all 29 exact again. He needed different numbers from her. He needed the same short list of them. His table, same shape of curve on the different person, steep to about 8 and then flat. One difference worth mentioning. He starts further ahead. E1 alone already captures 36% of him against 22% for her. This is because he sees further from the average face along direction E1 describes, so the first correction does more work. A warning that follows from there. If somebody hands you a compression scheme and quotes one example, ask for the distribution. Her 99% at 15 component and his 94 are the same method on the same ingredient. How well it does depends on where the individual sits relative to the population it was fitted on. One more, and by now the format should be doing the explaining for me. An average 29 fixed patterns and one number each. This face has the largest first amount of 3 examples. Watch how far one eigenface gets us. Plus 26.5 of E1, the largest of 3. 2, 68%, 3, 71, 4, 78%. The head tilt is what the early eigenfaces struggle with on this one. 5, 84, 6, 7, 8 eigenfaces, 91%, 6.5% off. Third set of amounts, same knee in the same place. 9, 10, 11, 12, 13, 14, 15, 94%, 16, 97, 17, 18, 19, 20, 3.5% off, and the 9 still to come will make a noticeable slice of a class to click through for almost no visible gain. 21, 22, 23, 99%, 24, 25, 100% to the nearest whole number. 26, 27, 28, exact. So 3 people, 3 leads of 29 numbers, one shared set of eigenfaces. That sentence is the lecture. Her table and the flattest start of the 3. E1 alone captures 53% of her, and there is a reason. And it is worth saying because it is the kind of thing that looks like noise until you look. Her head is turned slightly. The early eigenfaces handle head rotation poorly, so the middle of her sequence is slower than the other 2, even though the beginning was faster. The whole shape is the same in all 3 cases. Where exactly the knee falls depends on that person, which is the practical lesson from running 3 examples rather than 1. The average behavior is reliable. The behavior of any single case is not, and the thing that predicts it is how typical that case is of the set the model was built from. 3 people side by side at the same number of eigenfaces. Read this down as a column rather than across the row. At eigenface 1, the 3 are at 22, 36, 53%. They start in a very different places because how far a person sits from the average along the first direction is the fact about that person. At 8 eigenfaces, all 3 have converged to between 91 and 93%. Different starting points, same knee. After that, they are separate again. First woman reaches 99% by 15, the other 2 stall at 94. Every frame on this slide is built from the same eigenfaces in the same order. The only thing that differs between the columns is a list of amounts. There is a 4 column that is not on the slide, and that it is the one you should imagine. The face that was not among the 30. Eigenfaces still work on it because they describe faces in general rather than this particular person, but the reconstruction is a little worse. Any honest evaluation of a method like this has to be done on example it was not fitted on, and the gap between these 2 numbers is the thing to fix. Somebody always asks, how many eigenfaces are there really? The answer has 2 halves. The space of 128 by 128 pictures have 16,384 directions in it. So strictly there are that many eigenvectors, but only 29 of them carry anything. The other 16,355 describe directions along which all 30 of our photographs sit at exactly the same spot. There is no variation there to describe. Here is the giveaway that those are meaningless. They are not even unique. Any set of directions that fill up the leftover space works equally well. The software picks one arbitrarily. The real eigenface is pinned down by the data. The empty ones are pinned down by whichever linear algebra routine you happen to call. So why 29 and not 30? Students reliably guess 30. The rule is that n points always fit inside n minus 1 dimensions. 2 points always lie on a line, however big the room is. 3 points always lie on a plane. 30 photographs always lie inside 29 dimensional slice of space. And you can see exactly where the lost dimension went. We subtracted the average face. Once you do that, the 30 difference maps are forced to add up to 0 because that is what an average is. And that is one constraint, and one constraint costs you one dimension. 30 photographs, 29 dimensions, 29 eigenfaces. And the arithmetic agrees, which is always worth checking. These are the eigenvalues, the amount of variation across each direction. The first 29 runs from 8.17 down to 9. Different sizes, but all same order of magnitude, all cleanly real. The 30th measurement, 6 times 10 to a minus 14. That is a floating point dust. It is a computer's way of writing 0. So there is no 30th pattern to find, and no amount of extra pixels will conjure one. The limit is the number of photographs, not the size of them. Now let us go back and answer the question I asked you to hold on. Where did those patterns come from? Take one face, subtract the mean, and what you are left with is a map of how that person departs from the average. This brighter here, darker there. Do that for all the 30 and you have 30 difference maps. PCA never looks at faces at all. It looks at these 30 difference maps and finds the shapes that keep recurring across them. Notice where the structure is in these images. They are mostly flat gray with the detail on the edge face, the hairline, and the eyes. That is a preview of where the information lives, and it is why the eigenfaces look the way they do. Notice that this is where the alignment from slide 5 pays off, because the eyes are in the same place in every photograph. The difference maps are quite in the middle of the faces and busy at the boundaries. If the faces are not aligned, every difference map would be dominated by a bright rim where one face sits over another one, and PCA would spend its first several patterns describing the rim. The first 16 eigenfaces ranked. Each one of these is a real image, the same size as a photograph, and every face in this set is some mixture of them. The first 4 one alone, about 60.8% of everything that differs between these 30 faces. Watch them get busier and less face-like as you go down the ranking. The early ones describe broad things like lighting, overall shape. The later ones describe narrower things. And the tail E16 to E29. Each of these explain barely 1% fine texture, a stray lock of hair, the exact set of a smile. Together, E15 through E29 account for 10.8% of the variation. E30 is blank for the reason we just did. With 30 faces, there is no 30th pattern. Here is a question worth asking a class at this point. Which of these could you delete without noticing? That question is a whole of dimensionality reduction, and people answer it correctly by eye. This is the slide to slow down. A face is a recipe. Start at the mean face, add each eigenvalue in the right amount. The amount are the only thing that changes from person to person. Everything in the database uses the same E1, the same E2, the same E3. The numbers underneath minus 18.24 minus 11.04 plus 14.85 and so on are this person's entire identity as far as this model is concerned. If a student remembers one sentence from this lecture, it should be that one. The patterns are shared, the amounts are yours. That is also exactly why a face compresses so well. 2 consequences worth naming. First, this is why you can compare 2 people by comparing 2 short lists of numbers instead of 2 photographs. Second, if you were to hand somebody the amounts without the eigenfaces, they would have nothing. The identity and the ingredients are both needed, and only one of them is per person. This is the slide that earns the word linear. Start at the mean face, add minus 15.9 of E1, then minus 8.5 of E2, and then plus 7.7 of E3. Each step is the same move. Take an eigenface, scale it, and add it on. No multiplying faces together, no conditions, no if this then that. Scale and add, scale and add. Watch the bottom row as it goes. A person is already arriving by the fourth term, which means a face is a list of 29 numbers and you can draw it as a bar chart. Two people here and the same 29 faces for both. Everything that makes one of them, not the other, is in this height of these bars. If you want the equation on the board, it is face equals mean plus C1 times E1 plus C2 times E2 all the way to C29 times E29. The eigenfaces are an alphabet shared by everybody. The coefficients are the word that spells this particular person. And a bar chart is a very much smaller thing to store than a photograph. Most of the eigenfaces barely matter, and here is that stated carefully. The top row shows what each eigenface actually contributes to this face, all drawn at the same scale. By E18, there is nothing left to add. The first 8 carry 93% of her, and the remaining 21 carry 7% between them. The honest caveat about the bar chart: the amounts do not fall off perfectly smoothly, and one or two later components still carry something for this particular phase. A reliable measurement is that no single one of them mattered that much, so dropping the tail costs little. Throwing the small ones away is exactly what compression means. This is also a diagnostic. There is also a diagnostic in this picture. If the bars did not fall off, if 29th were as large as the first, that would tell you that the data has no grain and the PCA is the wrong tool. Looking at this chart before trusting this method is a habit worth having. Everyone rebuilt from the same 15 patterns, 16,384 numbers down to 15 numbers per person. That is a roughly a 1,000-fold saving. The honest footnote is on the slide. The 15 eigenfaces and the mean face have to be stored as well. And only once, however many you people have, add 1,000 more people, you still store 16 images plus 15 numbers each. That is why the technique scales, and it is exactly how face recognition worked in 1990s. You compare the list of amounts, not the picture, where the information actually sits as a bar chart of cumulative variance. E1 alone 27%, the first 5 66, the first 8 78, for the first 15 90%. The bar falls off a cliff, and that cliff is the entire reason PCA is useful. One caution, so that the number on this slide and the number in the rebuild sequences do not confuse anybody. The chart is variance across all 30 people. The percentages over the rebuild phases earlier were 1% at a time. Getting it to a true 95% of variance takes 20 of the 29 components, but the recognizable person arrives long before that. And the same chart, read differently, is a design tool. Decide how much of the variation you are willing to give up and read across, and you have chosen K. That is how the number of components get picked in practice on any dataset. Run it backward. Instead of measuring a person's amount, choose the amount yourself and see what comes out. Start at the mean face and dial each eigenface up and down. E1 is exposure, how brightly the photograph was lit. E2 decide whether the face is lighter than the background or darker. E3 controls how much dark hair frames the face. Nobody labels those nodes. Nobody labeled those knobs. Nobody told the method that lighting exists. PCA found them by looking at 30 examples, and that is what makes this learning rather than programming. If you have the interactive version open, this is a moment to hand it over. Ask somebody to make most extreme face they can, and then ask why it still looks like a face. It is also worth saying that what these knobs are not. They are not labeled categories. Nothing guarantees that a component matches a human concept. E1 turning out to be exposure is a fact about this set of photographs where lighting happened to be the largest source of variation. Fit the method to a set that was all lit identically, and E1 would be something else entirely. And here is the honest limit. These eigenfaces were learned from 30 human faces, so a face is the only thing they can build. Feed the model a cat, a card, or a pure static, and all three come back wearing the same ghostly expression even with all 29 components switched on. The model does not refuse. It does not signal that anything is wrong. It projects whatever you hand it onto the only thing it knows. The general lesson is worth stating plainly because it applies far beyond faces. A model trained on one kind of data will confidently produce that kind of data whatever you feed. That is the mathematics doing exactly what it was asked to do. There is an opportunity hiding in this failure. The model cannot tell you it has been handed a cat, but the difference between what you feed in and what comes back is enormous for cat and tiny for a real face. Measuring that leftover is how the same machinery gets used to detect anomalies, a topic of another day. There is a way to detect it though. Compare what you feed in with what came back. For a real face, the difference is small. For a cat, it is enormous. The model cannot tell you it has been landed a cat. The leftover can. Last section, everything you have just watched written down in notation in 6 lines. Nothing new happens from here. This is the same procedure written so that it can be checked and so you can implement it. A setup is on the slide. Each photograph unrolled into one long column of pixel values lives in 16,000 dimensional space. Mu is the average face, 1 over n times the sum. Each a sub I is a difference map, the photograph minus the average. Stack those numbers in a matrix A, which is 36,384. Note the line at the bottom. The difference maps sums to 0. That constraint is the dimension we lose, and it is why the answer is 29 rather than 30. The step everything else rests on. Turning a picture into a column of numbers. A photograph is a two-dimensional grid and linear algebra wants a column. So you read the grid row by row and stand it up. Do that for all 30, set them side by side, subtract the average, multiply the block by its own transpose. 2 things people trip over. First, unrolling throws away the fact that pixels have neighbors. PCA has no idea that the picture was ever two-dimensional. If you shuffled all 16,000 pixel positions, the same shuffle applies to every photograph. So you would get exactly the same eigenfaces with the pixel shuffled back the same way. The structure comes from correlation, not from the layout. Second, what a single entry of the product means. Row J column K answers one question. When pixel J is brighter than average is pixel K is brighter too. That product scaled by 1 over n is the covariance matrix C. Entry Jk is how pixel J and pixel K vary together across the 30 faces. Bright off diagonal means 2 pixels that brighten together. Opposite color means one brightens as the other darkens. The block structure you can see comes from neighboring pixel being strongly correlated, which is the visual signature of the redundancy PCA is about to exploit. One property matters more than any other here. C is symmetric and it is positive semi-definite. That guarantees a full set of mutually orthogonal eigenvectors with non-negative eigenvalues. That guarantee is the reason PCA always works. There is no initialization, no convergence, and no local minima to get stuck in. For scale, this matrix has 268 million entries and almost every one of them is redundant. Its rank is 29. And that is the same statement as everything else in this section, written in a different vocabulary. The eigenvalue problem itself, C times U sub j equals lambda sub j times U sub j. Each eigenvector U sub j is one eigenface, a direction in the space of the pictures scaled to unit length. They are mutually orthogonal, which means each one describes something the others do not. Its eigenvalue, lambda sub j, is the variance of all 30 faces along that direction, literally how spread out the data is. Sorting by lambda is what makes E1 the most important pattern rather than an arbitrary one. And lambda over sum of lambdas is the percentage printed under every eigenface in this deck. So the ranking you have been watching all hour is not a matter of taste. It falls out of the arithmetic. And notice what orthogonality buys you in practice. Because the directions are mutually perpendicular, the amount of E1 in a face that can be computed without knowing anything about E2. Each coefficient is one independent dot product, so adding a component never forces you to recompute the one that you already have. And the trick nobody skips in practice. You never actually build C. It is 16,000 by 16,000, so 286 million entries with a rank of 29. Almost all of it is structurally empty, and forming it would be slow and pointless. Instead, you build the small matrix G equals A transpose, which is 30 by 30. Solve that eigenvalue problem, then map each answer back with the formula on the slide. U equals A transpose V normalized. You get the same lambdas, same eigenfaces. The fact underneath is worth restating. A transpose and A transpose A always shares. They are non-zero eigenvalues, and A transpose A can have no more of them than A has rows. That single fact is both computational shortcut and the reason the answer is 29. And finally, 3 lines that are the whole deck. Line 1, C sub j equals U sub j transpose times x minus mu. That is the projection. It measures the amount of eigenface j in this face, and it is the dot product and nothing more. Line 2, x hat equals mu plus sum of C sub j, U sub j for j from 1 to k. That is the reconstruction, which is every rebuild sequence you have watched today. Line 3 is the interesting one. The average squared error you are left with after keeping k components equals lambda k plus 1 plus lambda k plus 2 and so on to the end. The error is exactly the eigenvalues you threw away, which is why the variance chart doubles as an error budget. You can keep how many components to keep before you rebuild anything. And one guarantee to finish on, no other flat k-dimensional subspace does better than this one. PCA is provably best linear choice, not merely a reasonable one. Take all 29 and the error bar 0 because nothing else has been discarded. That last property is worth dwelling on for a second because it is unusual. Most method in this course gives you something that works well in practice. This one comes with a proof of optimality among all flat subspaces of dimension k. The one PCA picks minimizes the squared reconstruction error over the training set. The catch is in the word flat, which is exactly what autoencoders and the nonlinear methods come in. 3 things to take away. 1. Data has a grain. Measurements that look independent usually are not. Height and arm span are 2 adjacent pixels or 2 sensor channels on a tool. PCA finds the few directions that data actually varies along. 2. A face is a short list, a mean face plus about 15 amounts. The patterns are shared by everybody, only the amounts are yours. 3. It only knows what it saw. 30 faces buy you 29 knobs, and anything that is not a face comes back as 1. The faces are the hook. The transferable idea is that most high-dimensional data is secretly low-dimensional, and same method is used to sort genes or to compress sensor data or to spot a wobble in a machine before it breaks. The recipe transfers without a single change. Whatever your objects are, write each one as a list of numbers, average them, subtract the average, find the eigenvectors of what is left. Keep the ones with large eigenvalues. The photographs were only there so you could watch it happen.